Don't, I think, wait.
Yes, started.
Ready to go, yeah. Okay, so welcome to the seventh lecture of number theory. Let us start where we left off last time, which is formats, not last little theorem.
Sir,
Say.
sir, before that, can you explain the magic trick? I couldn't understand with that video.
Okay, wait, I will explain it at the end of the class because I have to cover a lot of things. Okay, so Fermat's last theorem said that if P is a prime, then A to the power P is congruent to A mod P. This was our theorem, right?
Yes, sir.
So now we will prove it. Okay, now how will we prove it? We will prove it using combinatorics. And if you don't know combinatorics, I'll try my best to explain it to you in an intuitive way. Okay. Okay, so first, let us start with uh, numbers instead of variables. So let us say we have pearls. Okay, pearls, moti, जो भी है, of 5 colors. Okay. Now we make like this. We make a necklace of 7 pearls. Okay. We make a necklace of 7 pearls. So how many such necklaces can be there? First of all, see if this is my if I cut the necklace here. Okay, if I cut the necklace here, this is the string 1, 2, 3, 4, 5, 6, 7. I have 7 pearls in my string. Okay. Now this pearl can be either color. Okay, so let the 5 colors be red, green, yellow, blue, and white. These are my 5 colors. Okay. So this can be either red or green or yellow or blue or white, right? This pearl has 5 options. It can be any one of the 5 colors, right? Now suppose this pearl was red. Suppose this pearl was red. Then this pearl also has 5 options, right?
Yes, sir.
Yes, Dada.
Okay. Now suppose this pearl was not red. It was suppose some other color, say green. Okay. Suppose this pearl was green. Still it had 5 options. If it
Excuse
was blue,
me, I joined just now. Can you say what happened?
we are trying to prove Fermat's little theorem. Okay. So we are trying to prove Fermat's little theorem using combinatorics. And the first thing I assumed is we have pearls of 5 colors. These are my 5 colors. And I make a 7 pearl necklace out of these pearls. Okay. So if I cut this necklace here, then this necklace becomes a string, linear string. And each of these has 5 options. So what am I saying? is that pearl 1 has 5 choices. Pearl 2 has again 5 choices. And so on. Pearl 7 has 5 choices. Okay. So total, how many ways can I make this string? 5 into 5
The
into
5 to the
5.
power 7.
Yes. Acha, everyone understood this. Many people already know all this, but many people don't know. That's why I'm doing from basics.
Can you repeat once
Every,
again?
huh?
Can you please repeat once again?
Yeah. So what did I say? That the first pearl has 5 options, na? 5 colors it can be. For each of the colors, wait, let me draw a flowchart. Sorry. So color of pearl 1. Okay. It can be either white or it can be blue or it can be green or it can be yellow or it can be what red. Okay. Now suppose it is white. Okay. Then so suppose the color of my first pearl, this one, is white. Okay. Then my second pearl can be again 5 options: white, blue, green, yellow, red. Right. Understood?
Yeah.
Okay. But now suppose my first pearl is red. Then also it has 5 options. Second pearl. Suppose it is blue. Then also the second pearl can be 5 colors. So total 5 into 5 na in first 2 pearls.
Yes.
So if there are 7 pearls and I have 5 colors to color each pearl, then how many ways can I color the entire pearl? 5 into 5 into 5, 7 times. Right.
Yeah.
Okay. Okay. So this is basically 5 to the power 7.
Sir,
Okay. Huh.
sir, here repetition is allowed, right?
Yeah, wait, I'm coming to that.
Okay, sir.
Don't think too far because like many people don't even know this much and we are doing number theory. So let's
No, sir,
stick
I
to
was
the book.
asking because if repetition is not allowed, then sir, it would not be the case like that. So,
Yes, sir.
Yeah, yeah. Okay, so now what we do, we will remove all the uh, strings which are of the same color. Okay, so how do these strings look? One string will be there. There are 5 to the power 7 possible strings. Na? There are
yes,
5
sir.
to the power possible strings. Now out of them there will be one string where all the pearls will be white. Okay. Then there will be one string where all the pearls are blue. There will be one string where all the pearls are green. Okay. So what I am saying is I don't like same color strings. They are very boring. So I will remove them from my collection. Okay. So how many such strings will I get? 5 na? 5 for the 5
5.
colors.
Yes, sir.
Huh. So 5 to the power 7 minus 5 strings left. Right.
Yes.
Okay. Now what we do, these strings, now if I make the necklace, Now if I make the necklace, let me take a small example and show you. Suppose this is one necklace. This is a 3-string necklace. Okay. So if there is red, then there is blue, then there is green. Okay. And this is my string. And I attach them. Wait. Yeah, I attach them like this. Okay. So see, red, then if you go to the right blue, then you go to the right green. Here also red, then you go to the right blue, then you go to the right green. Right. So string, from this string, I made this necklace. है ना? From this string, this is a string. From this string, I made this necklace. Everyone understood how? I just connected the ends. Everyone understood?
Yes, sir.
Everyone.
Yes, sir.
Okay, okay. So now if I make this arrangement, first green, then red, then blue. Then if I connect the ends, then also this same necklace is formed now.
Yes, sir. It's just rotated a bit.
Yeah. So how many times can you rotate this thing and still get different necklaces? Number of pearls, na? Like if I had 4, say 1, 2, 3, 4, I can write them in a line like this: 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4. All these 4 strings will give the same necklace. है ना?
Yes.
Yes, sir.
O- Okay. So I had 5 to the power 7 minus 5 strings. Huh? But I have how many colors?
Sir, 5 colors.
5 colors.
Yeah. Wait, I think I made a mistake. There should be there are 5 colors, but like how many times can I rotate? I can rotate it since
4
it is
times.
a 7. No.
Oh,
For
for
our
that one, 7.
7 times, right? Okay, so let me just quickly say what I was saying. 5 to the power 7 minus 5 strings with different colors, because these 5 strings had same color, so we removed them. Okay. Now 7 strings form the same necklace. Okay. So how many necklaces can we form from this collection of strings? 5 to the power 7 minus 5 divided by 7, right?
Yes, sir.
Because we are counting each
So it should be an
necklace.
integer. The answer.
Yeah. Very good. So, see, we are counting each necklace. Each necklace can be made from 7 different strings. Okay.
Sir, I
So,
didn't understand this statement.
okay, so you understood this now? This
Yes, sir.
example?
Yes, sir.
Huh. So if I just increase to 7, then 7. Bas.
Okay, sir. Means okay. Yes, sir. I understand.
Okay. So like for 4, you have 4. For 7, you have 7. And I am counting them 7 times. That's why I don't want to overcount. So I am dividing by 7 again. Okay. So what is this? What is this quantity? This is number of necklaces with different colors. Right? Not different, let me say more than one color. More than one color. Okay. So if I am counting the number of necklaces, okay, it cannot be half, it cannot be pi. Can it be half or pi or something like that, or -1 or
No.
imagine?
Sir,
It
it
has
has
It
to
to
be a
should be
be
an integer. It should be a
the natural
natural
number.
number. Natural number.
natural number. Yeah. Okay. And integers, like natural numbers are integers, like all natural numbers are
Yes,
integers
yes, yes.
only. Not vice versa, huh? All integers are not natural, but all natural are integers. Let me just quickly draw Venn diagram. This is natural, this is integer. Integer is full, including
A
natural.
whole number.
A whole is just thoda sa, I think 0 element but extra
Yes,
hai.
yes.
Okay, so this is the number of necklaces. So this has to be an integer. So 5 to the power 7 minus 5 by 7 is an integer. So can I
Yes,
say 5 to the power 7 is congruent to 5 mod 7?
yes, sir.
Yes, sir.
Okay, now replace 5 with A, 7 with P, and repeat this entire argument, you will get Fermat's little theorem.
Sir, so is it the proof?
Yeah, this is a
No, sir, the
proof. This is,
necklace one. Necklace.
like I use numbers because you are doing combinatorics for the first time. If I was doing it after a combinatorics class, then I would directly do with A and P. But
Okay, sir.
since many of you don't know combinatorics, I just took an
Sir, I thought
example.
that the actual proof was this, the necklace.
necklace one is actual proof. क्या हुआ? विश्वास नहीं हो रहा.
No, sir,
Hello.
means I, I
हाँ.
I need a mathematical proof.
Yeah, like
And
what makes you think this is not mathematical? Like, is
I said
there any?
that's what I'm saying.
This is perfectly logical. There is no flaw in this proof.
Yes, sir. Yes, sir.
Like, the only flaw is that I used 5 and 7. If you do with A and P, then there will be no flaw. I did with 5 and 7 because you don't know combinatorics. Like if you repeat, like if I divided by 7, now I will divide with P because like a necklace is P pearls long. Okay. So you can rotate it P times to get the same string. That's why you will divide with P. Then there are A colors. Basically, how many necklaces are there formed from pearls of A colors uh, and P pearls long, such that the necklace is not made of only one color. Okay, what is the answer to this question? A to the power p minus a divided by p. Okay, and since this is the answer to a question which you can count, this belongs to integer, hence a to the power p is congruent to a mod p. This is the proof. So like basically you have a colors and p pearls long necklaces. That is the actual proof. Okay, everyone understood this proof?
Yes, sir.
Everyone, matlab everyone. Anyone did not understand,
To
please
make
tell
this
me.
proof as the homework, I did it using another way. Like I showed that if I took 7 and 5 as an example, and I showed that every remainder means every other number which doesn't divide, which isn't a multiple of 7, the remainders will be the permutations of this, means the re- the the mod value.
I did not understand. Can you repeat? Hello?
Yeah, yeah.
Ah,
I just showed that all of them are a rearrangement, but not in the Pearl way. Like I showed it using inequalities and algebra.
acha, okay, no problem. Like there are many proofs of Fermat's little theorem. There is even one proof using induction, which you should try. But like I found this proof the most beautiful proof because there is hardly any maths here. There is only counting some pearls and colors and like, it's like very less maths and more like real thing. And still we proved such a very like Fermat's little theorem, which is so much maths feeling. Like Fermat's little theorem does not sound like something you will encounter in daily life, na? That somewhere in my daily life I will encounter that a to the power p is congruent to a mod p. ऐसा थोड़ी ना होता है. But the proof is so simple and using daily life things that's
So why
why
this
I found.
theorem is known as Fermat's little theorem?
Format
Why?
because Format made it and little I don't know, most probably because he had bigger theorems. He was a very great mathematician, so he had a lot of
Yes, sir,
theorems.
that I know. But why the name he kept the name as little theorem?
I don't think the mathematicians keep the names themselves. Uh, like how do I say? Even Euclid's division lemma thing. Did Euclid name it that this is my division lemma? This should be called
No,
Euclid's
sir,
division.
anyone. No, sir, anyone
Ha,
who. Uh,
like in later maybe someone did that, but why I don't know. You can Google and you can post it in the Discord group and let us know, please. Okay, interesting story. But I don't know. That is my answer. Okay, so today like we will do number theory, but with a bit of combinatorial flavor. For example, we just did this proof. Now, like here is like I don't know what rule or something. If you can count, it is an integer. Obviously, na. If you can count, it is an integer. 1, 2, 3, 4. I am counting like that. You can't count real numbers, na. Like if I ask you, what is the number after 0? What is the real number after 0? Can someone tell me?
sir, can you repeat?
What is the real number which comes just after 0?
That there are many, sir, infinite,
Then
sir, between 0
infinite.
to 1.
Yeah, like if I say 0.1, then you can always find a number between 0 and 0.1. So my answer is wrong. Okay. Now you can always find a number between the number you found and 0. So it will be even smaller. Then you can go like as small as you want, but you will never reach an end. So like it does not make sense to count in real numbers. Like numbers are not for counting. Numbers started because of counting, but as we develop the other types of numbers like fractions, then irrational numbers, real numbers, complex numbers, like counting is hardly a criterion for something to be called a number. Okay. So what this rule is saying is that if you can count, then it is an integer. Not even an integer, natural number. And when you learn a bit more combinatorics, you will be able to solve many number theory questions also using this rule. Acha, there was one question in the interview for this year, I think, using this rule only. I don't remember the question.
Sorry, sir, what else?
There was a question using this rule in the Maths Club interview this year. I don't remember the question. But basically what I'm saying is when you learn a bit more combinatorics, you will be able to apply combinatorics in number theory also.
Sir,
For
yesterday's
example,
POTD was based on Fermat's little theorem.
acha, I did not see. Acha, so uh, how to use this rule? We just now did one example, which is Fermat's little theorem. Okay, we can count the number of necklaces. Like if I randomly tell you that a to the power p minus a by p, where p is a prime, tell me something about this number. Tell me, fast. You won't be able to say anything, na? Like
Sir, it is
how,
an integer.
yeah, like that you know now, but before yes, before Monday's class, how will you tell? Like you don't know. So basically, what this rule is saying is, if you can express this number, if I can express this number as the number of ways to blah blah blah, then it is an integer. Okay, you don't need any number theory. You can do it using combinatorics only. Like we did here using pearls and colors. We did not use any modulo, we did not use any induction, nothing we used. We just counted number of pearls of some color arrangements and so on and proved that it is integer. Acha, the meeting will end in 10 minutes, by the way. Just inform me. Please rejoin after it ends. So if I can express it as as the number of ways to do something, then it must be a natural number. Another example would be uh, prove that n factorial by n minus r factorial is always an integer for 0 r n. R and n are natural, not natural whole.
So do we have to prove it?
No, I am asking you how will you do it? Like
Sir,
one
can
thing
I
you
tell?
can, you know combinatorics, na?
Sir, I can just basic means I can easily tell it, like anyone can understand it maybe.
Okay, say.
Sir, n factorial, you told that n factorial is nothing but n into n minus 1 into n minus 2 dot 2 into 1. And sir, n minus r will be n minus r into n minus r minus 1 into dot till 2 into 1. Now, sir, as r is less than or equal to n, So sir, when we expand n factorial, there must be a term, means there must be a term n minus r plus 1, as n is
Oh,
greater.
wait, let me make the question a bit complex. Now do it. The first one was very easy.
Okay sir. Now I have to think.
Okay. So let me just tell you, because you people don't know combinatorics, but just remember this when you study combinatorics, that I can use combinatorics in number theory also. You will learn later. So basically, if you have, again, let us do it by small example. Let us take r equal to 2, n equal to 4. Okay. So suppose you have two boxes, huh? And in each box, wait, not like this. Wait, just huh. Okay, so you have suppose four chocolates, one, two, three, four. Chocolate one, chocolate two, chocolate three, chocolate four. In how many ways can you pick two chocolates? Okay. So suppose this is my blank for chocolate one, this is my blank for chocolate two. Chocolate one has four choices. Everyone agrees? Chocolate one. This
Yes
is
sir.
chocolate. What I pick in my first chance. This is my chocolate two. Okay, so suppose I pick chocolate one as one only. So one is gone. Now I have to pick another chocolate from the remaining three. So chocolate two has three choices, right?
Yes sir.
Hey, everyone else say yes, sir, please.
Yes, sir.
More people, more people. Only two, three are attending class, it seems. Okay, do we have? So chocolate one into means four choices for chocolate one. If I choose one, then there are three remaining choices for chocolate two. So total I have 12 ways to pick chocolate one and chocolate two, है ना? But now see, if I first pick one, then I pick three. Okay. And if I first pick three and then pick one, like if I first pick chocolate one, then chocolate three. And if I pick chocolate three, then chocolate one, then these two are same for me, na? How does it matter which I
Yes,
pick
sir.
first, which I pick last? I am getting to eat chocolate one and chocolate three. I am happy. Okay. So then what is the answer for this? 12 divided by 2, because I am double counting everything. Similarly, you can show that this thing is just the answer for n chocolates, and you have to pick r chocolates. There are n chocolates given to you and you have to pick r of them. How many ways can you do it? You can do it in this many ways. Okay. Homework complete. I have told you for n equal to 4, r equal to 2. You have to generalize this for any n and r. This is your homework. Okay. And in the binomial theorem, you learned this thing, NCR.
Yes sir. N choose R.
That is basically this thing only, n factorial by r factorial into n minus r factorial. And what does n choose r mean? N choose r. means n chocolates given, I choose out of them. Okay. In how many ways?
What is this sign? CNR.
Theory, but still with a combinatorial flavor. Now we will count how many factors a number has. Okay. So suppose there is a natural number n. I am again using a fundamental theorem of arithmetic. This is my number n. Okay. Question is how many factors does it have? Let us start with a simple example. Let n equal to 12. Okay. Now someone prime factorize 12.
Sir, 2 square into
so
3.
Wait.
Sir, it can be infinite.
Just a minute. My audio got disconnected. I cannot listen to you. Please wait for a minute.
Hello.
Can you show the question again? I got disconnected.
Hello.
Yes, sir.
Hello. Am I audible now? My
Yes, sir.
Yes, sir.
earphones got disconnected. Everyone in? Anyone left? No, I think.
Can you scroll up to the question? Yeah, thank you.
So what is 12? 12 is 2 square into 3, na? 3 to the power 1. Right. Now, someone tell me all the factors of 12.
So there are infinite factors.
Eh?
Sir, 1, 2, 3, 4, 6, 12.
Yeah. Why infinite? I don't know.
Can you just scroll
It
up
can't
once?
be, sir, can't it be written as 24 to the power 0?
Yeah, but that is 1, na? 24 to the power 0 is 1. Like, however you write it, the value is 1.
Okay, sir, I
Your,
got it.
your representation may be different, but the number is still 1.
I got it, sir.
Hmm. Okay. Okay, so factors of 12. Now let us write this in a good way. 1 is 2 to the power 0 into 3 to the power 0. Okay. Then the second one is 2 to the power 1 into 3 to the power 0. Third one is 2 to the power 0 into 3 to the power 1. Fourth one is 2 square into 3 to the power 0. Fifth one is 2 to the power 1 into 3 to the power 1. And the final one is uh, 2 square into 3. Okay, these are the factors now. Someone just like, not someone, everyone just confirm. Like,
Yes,
you
sir.
understood?
Yes,
This
sir.
is 1. This is 2. I have just written all of them using my this theorem, fundamental theorem of arithmetic. In that notation, I have written nothing else. Now, if I write 2 to the power a into 3 to the power b, okay. Now, if I make a table of like what are the possibilities? A is 0, 1 or 2.
So 0,
B
1, 2.
can be 0 or 1. See,
Yes,
A
sir.
here is A is 0, A is 1, A is 2, A is 1, A is 0, A is 2. Okay. Similarly, here B is 0 or 1. 0, 0, 1, 0, 1. This is again 1. So, what am I saying is that your number can be P1 to the power E1. It can have P1 to the power E1, but your factors will have P1 to the power 0 also, P1 to the power 1 also, P1 square also, till all the way up to P1 to the power E1. It will have all possibilities, right?
Yes, sir.
Okay. So now let us take another big example. 2 to the power 10 into 3 to the power 15 into 5 to the power 17 limit. Okay. Suppose n is this. Okay. So tell me, 2 to the power x, 3 to the power y, 5 to the power z divides n when?
Sir, can I tell?
No, someone else, please.
Sir, when n is equal to 7xy.
N equal to 7xy. No. Acha, 5 to the wait, this will be z. Wait, just a minute.
Sir, xyz.
Xy. Okay, so n, if n divides this, then n by this is an integer. So 2 to the power 10 into 3 to the power 15 into 5 to the power 17 divided by 2 to the power x into 3 to the power y into 5 to the power z is an integer. When is this an integer? When they will perfectly cancel away, na?
Yes,
If
sir.
there
Yes,
is
sir.
something, if there is something remaining, then it cannot cancel, and there will be a denominator which is greater than 1, and it will become a fraction, right?
Yes, sir.
So x less than equal to 10, greater than equal to 0. Similarly, for y it is 15, and for z it is 17. Everyone agrees? All these three have to take place together. Then only this will be a factor. Everyone got it?
Yes, sir. Sir, where x, y, and z all are natural numbers.
Huh.
Sorry, integers.
Yeah. Okay. Also, if you have to, if suppose t is a factor of n, then can t have any prime other than 2, 3 or 5?
No, sir.
Yeah. So like if my t is very small number, still it cannot be a factor because it will not cancel only. It will be a improper fraction, but still it will be a fraction because it is not cancelling. So this is my lemma. For n equal to p1 to the power t1, p2 to the power e2, pk to the power ek. Okay. Divisor or factor of n are of the form d equal to p1 to the power f1, p2 to the power f2, pk to the power fk, where f1, f2, fk are integers such that 0 f1 e1, 0 f2 e2, and so on. Got it? We just generalized this thing. We started with 12 only, huh? We started with 12, but we generalized it to this. This is our lemma. Remember this. Okay. Everyone, please note this down. Understood till here, I hope.
Yes, sir.
Okay. Everyone in? Anyone blanked out or anything? Please tell me.
Sir, could you please keep the screen like that? Actually, I am copying it.
Acha, everyone is understanding to.
Yes, sir.
अरे तो क्या बोली तू?
Yes.
Yes.
अरे तो क्या बोली तू? Only 3-4 people say yes, yes. जो भी हो. Okay. So now, how many factors? How many factors? If my factor d is of the form p1 to the power f1, p2 to the power f2, pk to the power fk. Okay. So f1 can be 0, 1, 2 till e1. f2 can be 0, 1, 2 till e2, and so on. Na? So
Yes, sir.
f1 has e1 choices. f2 has not e1, 1 plus e1, because see, 1 to e1 is e1, and then another 0 also we have. So we have e1 plus 1 choices for this power of the divisor. Okay. Basically, let me compare it with the 12 case. So 12 was 2 square into 3 to the power 1. So if I consider only the power of 2, any divisor d of 12 equal to 2 to the power a into 3 to the power v, where a equal to 0, 1, 2. So it had 3 choices, right? If the power was 2, it had 3 choices. If the power is e1, it has e1 plus 1 choices. Let me write that in a better handwriting. E2 plus 1 choices and so on. Okay. So what is the number of factors? Is just how you can choose the powers, na? Because each choice of powers will give you a new factor, right?
Yes, sir.
Everyone understood? Okay.
Sir,
Huh.
then will the total number of factors will be E1 plus 1 into E2 plus 1 dot
Yeah,
dot
yeah.
EK plus 1.
Yeah, exactly. So total number of factors of this is the formula. Okay, so now someone quickly tell me number of factors of 72. Calculate this and tell me the answer. I'm giving you 1 minute.
Sir, can I tell?
Yeah. Tell me the
Sir,
full
12.
method. Huh?
Sir,
Huh?
method also, right?
Yeah.
Sir,
First,
sir, answer will be 12. So, sir, here 72, we can factorize it as 2 cube into 3 square.
okay.
So, sir, maximum powers are 3 and 2. So, sir, it will, the number of, total number of factors
Sir,
will
E1
become
plus
3
1
plus
is
1.
3 plus 1
Yes,
into
sir, it's 2 plus
2
1. So,
plus
sir,
1
it
with
will
it
be
12.
4 into 3. So, sir, 12.
Okay, very good. Also, now if you try to list out these 12 factors without like from the a combinatorial point of view, not from the numerical point of view. Like 2 to the power 0 into 3 to the power 0. 2 to the power 1 into 3 to the power 0. 2 to the power 2 into 3 to the power 0. 2 to the power 3 into 3 to the power 0. Okay. 2 to the power 0 into 3 to the power 1. 2 to the power 1 into 3 to the power 1. 2 to the power 2 into 3 to the power 1. 2 to the power 3 into 3 to the power 1. Similarly, last row will be 3 square karo. Okay, these are all the factors. This is how you count them. Okay, now there is this interesting question. Suppose there are 1,000 doors. Okay, doors only.
So can you repeat?
Wait, 1,000 doors. Dorja, dorja.
Okay, okay.
Okay, and there are 1,000 people. Each person has a number. Like there is a person number 1, there is a person number 2, person number 5, person number 50, and so on. Okay.
Okay.
Huh. So what person number 1 does? Person number 1 goes and opens all the doors. They were closed first. Okay.
For all the doors.
Yeah. Person number 1 goes and opens all the doors. All the doors were closed. He goes and opens all the doors. Then person number 2 comes. He all the doors are open now, na? So he only closes the even numbered doors and does nothing with the odd numbered doors. Okay. Now person number 3 comes and only changes the state of doors which are divisible by 3. So like door number 3 was open, so he closes it. But door number 6 is closed, he opens it. Door number 9 is open, he closes it. Then 12 is closed, he opens it. So on. Okay. And then from similarly 1,000 people do that. Like person number n goes and opens or closes the doors which are which are divisible by n. So person number 50 only touches the doors 50, 100, 150, 200 and so on. And what each person does is, if the door was already open, they close it, and if the door was already closed, they open it. Okay. Now, after 1,000 people have done this thing, how many doors are open and how many doors are closed? This is the question.
Can I see?
Huh?
It will be all the prime numbers are open.
Why?
Because all of the other ones are just a second.
Sir, what we have to find, can you tell again?
How many doors are open and how many doors are closed after 1,000 people have done this?
Okay, sir.
Spandan, you were saying something?
How many doors will be closed, right? Or how many doors will be
Eh,
open?
You can answer any. I don't
Just a
care.
second.
Like,
Let me cross check once.
I just only care about your logic. Like, how many open, how many closed, that is the 1,000 minus the other one.
Sir, I think all the
Acha, this is a bit hard and like,
sir,
let me
I
do
think
it. Okay.
all the prime numbers were all the prime number doors were closed.
Why?
So because the first person means open all the door, and the person whose door it was closes it. So as it is a prime number, so there would be no other person who can open or close the doors. So all the prime number doors were closed.
Okay. But like, are they the only ones that are closed, or there are more, or there are less? How do you know that?
No, so
Like,
there
you
would
know.
be more, but
Okay.
all the prime
Okay.
numbers would be closed.
Acha. Yeah, you are right. But there will be more. Like
Sir,
all the
one
primes
will
are
also be there.
Yes, sir. They
okay, but still there will be more. Okay, let me solve this question, because like, or you want it as problem of the day, in which case I can leave it
it's
here.
given.
Okay, so let me solve it only. Just increase the brightness. Huh. Okay, so think from the perspective of a door. Say I am door number n. Okay, I was closed first. Okay, so after 1,000 people have done their job, what decides whether I am open or I am closed? If I am open, then I have been touched odd number of times, right? And if I am closed, then I have been touched even number of times. right?
Huh?
Okay. So suppose the door was wait. So door was closed. Okay. Now it was touched once, then it becomes open. Then again touched, closed. Again touched, open. Again touched, closed, and so on. So like closed is 0. After one touch it is open. After two touches it is closed. After three touches it is open. After four touches it is closed. So after even number of touches I am closed. After odd number of touches I am open. Okay.
Yeah.
Yes, sir.
Okay.
Yes.
So what decides how many times I will be touched? Who can touch me? Who can touch me? First of all, say who can touch me.
My factors. Like the
Yeah,
door.
only my factors are allowed to touch me. That is point number 1. Only factors can touch me.
So we need to find all the factors of all the doors.
Wait, we don't need to find factors. Acha. Now what decides if I am open or closed? How many times I have been touched? Nah,
Yes, sir.
Yes, sir.
it is odd or even. And how many times I have been touched? How many factors I have, right? Like if I have 5 factors, I have been touched 5 times by all my factors once. Yeah, if I have 50 factors, then all the 50 factors come and touch me once. Right?
Yes, sir.
Number of touches equal to number of factors. Okay. So now we have to just analyze when number of factors is odd and when number of factors is even. Number of factors. If it is odd, then door remains open. And if it is even, then door is closed. Agreed?
Yes, sir.
Okay. Now, if n equal to p1 to the power e1, p2 to the power e2, pk to the power ek, okay. So, number of factors equal to, we just now proved this.
Yes, sir.
Okay. Now, when this expression is odd, the door remains open, and when this expression is even, the door remains closed. Everyone followed till
Yes.
here? Because this is only my number of factors. Okay. So if this, okay, so this is k many terms na, e1 plus 1, e2 plus 1, ek plus 1. This has k terms in the product.
Yes, sir.
If even if one of the terms is even, okay, even if a single one of them is even, it does not matter if the rest of them are all odd, the product will become even, right? Like if I multiply 5, 7, 3, 39, whatever odd number, how many ever odd numbers you like, you multiply, but even if there is a single 2, the entire product is even, right?
Yes, sir.
Yes, sir.
Okay, very good. So if I want this entire product to be odd, then each of these bracket terms are odd, right? This is odd, this is odd, all of them are odd. Then only the product is odd.
Yes, sir.
Okay. Now if all of them are odd, E1 plus 1 is odd. Then E1 is even, na?
Yes, sir.
Okay.
Yes,
Similarly, E2 is also even. EK
Yes,
is
sir.
also even.
Yes.
Acha, now if in a number all the powers of the primes are even, then what is that number? Isn't it a perfect square?
Yes, sir. It is
Yes,
perfect.
sir. Yes, sir. It will be a perfect square.
So which doors remain open? Only the perfect
Sir, only
square doors
perfect.
remain.
Yes.
Yeah, very good. Only perfect square doors remain open. So from 1 to 1000 जितने भी perfect square है, I don't know how many, 31 I think. Only those will remain open bus. Like in general from 1 to n if you want to do, then take the square root of n, round it down. That will be the number of doors open.
Yes, sir.
For 1000 it is 31. The answer is not important, the process is more important. How we understood that it is 31. Why only perfect square? Only perfect square has all these powers even, so the number of factors for perfect squares are odd, and for any non-perfect square the number of factors is even. Okay, this is the moral of the story. Now let us do we now did number of divisors. Now let us do sum of divisors. So each divisor, acha, first again n equal to,
Sir,
so
is it
you are
always zero?
what?
Sir, sum of divisors of any number would be zero, right? Or
No, why?
sir,
Oh,
because the number can be divided by the negative of it number. Like
Are
12 can
ha.
be.
So like divisors, we only take the positive, na.
Okay, sir.
Like
Then sir.
ha. Like in number of factors also we only did see from positive only. Like we can for 12 also we can take -1, -2, -6, -12. But here we are dealing with positive only.
Okay, sir.
Also
I
this
got it.
this meeting will again end in 10 minutes. So after it ends, please rejoin. I will send the link.
How did you generalize that door sum?
So basically number of doors does not matter na. Number of factors matters. So all perfect square doors will remain open. So like for 1000 there are 31 perfect squares from 1 to 1000. Now if I ask you from 1 to 100 there are 10 perfect squares. So similarly you have to just calculate number of perfect squares from 1 to n. That will be the answer for n doors. That is the generalization,
Oh, okay, got it.
which is given by like square root of n, and you take the box function. Like what is the square root of 1000? It is 31 point something, na.
Yes,
Yes.
sir.
So if you round it down, then it will be 31. So similarly, you have to take the box function of root n. Box function, floor function, जो भी बोलना है बोलो. Also, floor function will be taught to you in detail in number theory only. Coming soon, but not today. So you are seeing now how important fundamental theorem of arithmetic is. We are using it so many times in so many questions, so many ways. It is like the backbone. It is like primes are the building blocks of all numbers, because any number can be factorized into primes. So fundamental theorem is very important. Okay, so sum of divisors. Divisor D is of the form D equal to P1 to the power F1, P2 to the power F2, Pk to the power Fk, where 0, F1, P1, 0, F2, E2. This one you understood only when we were doing number of devices, right?
Yes, sir.
Okay. Okay. So now let us just do a bit of algebra plus combinatorics, just a small diversion. What is the expansion of this?
That
AX
AX,
plus
BX,
BX
BX
plus C
plus
plus AY plus BY
that
plus C.
AY, BY, AY plus BY plus CY.
Wait. Huh. Okay. Now tell me how many terms are there?
6.
So
Okay.
6 terms.
How many terms are there in this expression?
So
3.
3.
How many in this?
2.
So 2.
What is 3 into 2?
So
6.
6.
Magic. It is not
Yes,
magic,
sir.
it is like, can you justify why this happened? And this will happen for any, like, if you do anything, it will happen. It is not like a coincidence. If I take A plus B plus C plus D plus E into P plus Q plus R into X plus Y, then this expansion will have 2 into
2 into
5
5 into 3.
to 3 जो भी है 30 terms.
30.
But why will it have
Sir,
30
can
terms?
I tell?
Justify. Okay, you say.
Sir, if I take the last one, sir, X plus Y into A plus B plus C plus D plus E. So, sir, into P plus Q plus R. So, sir, now if I take first P plus Q plus R into X plus Y. So, sir, with X, there will be 3 terms in the expansion, and Y with Y, there will be 3 terms. So, sir,
Yeah.
it will become 3 plus 3, 6 terms. So, sir, 3
Hmm.
into 2, 6 terms.
Yeah.
Now,
Similarly,
sir,
okay, got it. That is just
yes, sir.
repetition. So again, we are using that argument which we used while doing necklaces, like x plus y into a plus v. So think from the perspective of a variable. Suppose you are x. Think that you are only x. I am x. My name is x. I am inside this bracket with my friend y. There is another bracket which has a and b. Now I have to get multiplied with them. So how many times will I get multiplied? I will once get multiplied with a. I will once get multiplied with b. Okay. Now if there is another term c, then I will be multiplied with another term c also. Okay. So if there are p terms in this bracket, then if I am x, I will get multiplied p times, na? One term will be ax, one time will be bx, then cx, dx, so on. Understanding? Like I am getting multiplied with this, I am getting multiplied with this, I am getting multiplied with this, I am getting multiplied with everyone. Understood?
Yes, sir.
Yes,
Okay,
sir.
so now if I am y, then also same thing will happen with me.
Yes, sir.
So if this has q terms, then the each term will have p terms in the multiplication. So there will be pq terms in the multiplication, right? Everyone understood?
Yes, sir. Yes, sir. Yes, sir.
Like if I am x, I will have p terms. If I am y, I will have p terms. If I am z, I will have p terms. Similarly, there are q many variables, each has p terms. So p into q हुआ ना? And what are
Yes, sir.
these terms? These are all possibilities of multiplication. Everyone is getting multiplied with everyone. in other bracket, like x and y will never multiply, but x will get multiplied with everyone in other bracket, y will get multiplied with everyone in other bracket. Like all variables get multiplied with everyone in other brackets and no one in their own brackets. Can you understand this thing?
Yes, sir.
Everyone understood, or should I repeat? This is again combinatorics territory, so like I'm going slowly. Everyone understood?
Yeah.
Acha, okay. Okay, so now what is a factor? A factor is of the form this thing, where again I have to generate all possibilities for all these possibilities, right? Okay, so now let us see this expansion. 1 plus p1 plus p1 square till p1 to the power e1 multiplied with 1 plus p2 plus p2 square till p2 to the power e2 multiplied, like there are k terms like this. If you multiply this entire expression, what will you get? You will get sum of all the factors, na?
Yes.
Because it will have all possibilities, like any term of this product is of the form p1 to the power f1, p2 to the power f2, and so on. Now f1 maximum value can be e1 only. It can be 2 also, it can be 1 also, it can be 0 also. Like I have included all the possibilities in one bracket. Now if I get, this is the possibilities for p1. Now these are the possibilities for p2. Let us take a small example. Uh, Again, let us so 12 ka prime factorization, what is? We have done it so many times. 12 seems to be
2
like
square into
our
3.
favorite number only. 2 square into 3. Okay. Now if I write this 1 plus 2 plus 2 square into 1 plus 3, and if I multiply, don't multiply using the values, multiply using algebra. Like distributive property, if you apply, then what is the product? 1 into 1 is 1, plus 1 into 3 is 3, plus 1 into 2 into 1 is 2, plus 2 into 3 is 2 into 3, plus 2 square into 1 plus 2 square into 3. Aren't these all the factors of 12?
Yes, sir. They are.
Okay. And did you understand how we got them? Like if we, whenever we multiply two things algebraically and use the distributive property, everyone in one bracket gets multiplied with everyone in the other bracket in all possible combinations. This is what happens. So we are just exploiting that property and saying that in general it will be 1 plus p1 square till p1 to the power e1. p2 to the power e2, and so on till pk. This is my sum of divisors. This is the
Can you
formula.
again explain it?
What?
Can you again explain it?
From where?
From the previous section where you wrote this same expression.
Acha. Wait. So see, x plus y into a plus b. When you multiply, what is happening? Everyone in this bracket is getting multiplied with everyone in this bracket, right?
Yeah.
To give all possible combinations.
Yes.
Okay, so what is a divisor? Like how to generate divisors of a number? P1 to the power f1, P2 to the power f2, and so on. And you have to just find all possible combinations, na? Just all possible combinations of f1, f2, and so on. You will get, then all those are the divisors only, right?
I couldn't understand.
Huh? Like, wait. For 12, what are the divisors? Tell me. Like 12 is 2 square into 3 to the power 1. So if D is 2 to the power A into 3 to the power B and D divides 12, then AB lists the values of AB.
1,0,1,1,0 means there will be the which we derived earlier.
Like all possible combinations, na?
Yeah.
All possible combinations
For a equal
for
to less than equal to 2 and B
very
equal
good,
to
very
1.
good.
Less than equal to 1.
Yeah, very good. Okay. So now if 1 plus uh, 2 plus 2 square into 1 plus 3. If I open the brackets and multiply using distributive property, okay, not like this is 1 plus 2 plus 4, 7 into 7 into 4, 28 directly, not like that. If I think these are variables and multiply using distributive property, what will I get? Tell me each term.
1, then
Huh?
again, a second, 1 plus 2.
Huh?
Hello, am I audible?
Yeah, you are audible.
Okay.
1 plus 2,
1 plus
then
2 plus 2 square
huh?
plus 3
Okay.
plus 3 into 2
Huh?
plus 3 into 2 square.
Okay. So, like what we did, we all possible combinations between these two brackets, na?
Yeah.
So, and what are these all possible combinations? These are just divisors. Like this is a factor, this is a factor, this is a factor, this is a not this. This is a factor, this is a factor, this is also a factor. Understood?
Yeah.
Okay. So, like, so similarly, if I do this for, let me not rewrite so many times. So if I just use this formula, 1 plus P1 plus P1 square, P1 to the power E1, then P2, P2 square, P2 to the power E2, and so on till Pk to the power Ek. And if I open all the brackets, what will I get? Won't I get the sum of all possible combinations of
Yeah.
powers? So that is the sum of divisors only, na?
Yeah, got it.
Okay. So uh, so there is this mathematician called Mersin. Okay. So he said that like you can find many primes like this. Can you give me some examples for m equal to 2? Wait, let me just make a table. Here are m values, here 2 to the power m minus 1 values. When m is 2, what is this? 3. When m is 3, what is this?
7.
Sir,
7.
7.
Then for m equal to 4,
Sir, 15.
15. 15 is not a prime. So this case we are ignoring. Then m equal to 5,
Sir, 31.
31 is a prime, na?
Yes, sir.
M equal to 5, 31. And so on. Like you will get many primes like this. Okay. And uh, like you know na that computer scientists try to just find new prime numbers. You read about that cryptology and encryption in the first lecture of number theory, how your WhatsApp messages are encoded and all.
Yes, sir.
Yeah, so like what do? They have a key. Your left. Okay, so like if I give you some number like 15, you don't know it is prime or not. Like you know, obviously it is 3 into 5 made up of 2 primes. But if I just start writing 5, 6, 7, 2, wait, my screen share stopped. Huh. 9, 1, 0, 6, 7, 8, 5, 2, 3, 4, 6, 9. If I just start writing and like I write a random number like this, how will you know it is prime or it is made up of primes, and how will you factorize it like this? Like you have no way except brute force, na? How do you factorize 15? Tell me, how do you factorize 15? How do you know 3 and 5 are factors?
We check for divisibility.
Yeah. So like if I give you a big number, say 280, how will you factorize it? You first check it with 2. If it works very good, you again check it with 2. Works again very good. You keep checking with 2 till there is no more power of 2. Then you check with 3. Then you check with 5. Then you check with 7. Like you check with prime numbers, like you just keep checking, na? You just keep checking till you completely factorize it in terms of primes. So what is this checking? You are not being intelligent. You are just like this is just brute force. You are trial and error basically. You are just trying every prime number. If it works, you are writing it down. There is no intelligent method as of now. Like even the best mathematicians factorize numbers like this only. There is no intelligent way out. Okay. So if I give you suppose a 200 digit number, which is of the form P1 into P2, where P1 and P2 are primes. Okay. And you do not know what these primes are, then you cannot factorize this number. So what this encryption does is like the sender has the primes, the receiver has the primes, like only they can encode and decode this. But like if someone, say a hacker, that person intercepts your message, then they have to guess these primes, then only they can factorize the number, and if they factorize the number, then only they can look into your message, or else they cannot read your message. That is like how encryption works. So if they have to guess this number, they have to try every 200 digit number, they have to try using a computer, because there is no intelligent method. So if I have very large prime numbers, that is good for us now, that we won't be hacked easily. If we have large prime number collection, then we have less chances of being hacked. That is why like computer scientists just keep on finding new primes. So first what was done, like suppose you know all the primes till 1000, then how do you factorize 1000? find more primes. You see 1001. Is it a prime? 1002. Is it a prime? 1003. Is it a prime? Again, there is no intelligent method. You just keep checking manually. But after, like now what they do, they just put values of m here and generate new primes, because you don't have to check in between now. Like between 7 and 31 there are many primes, but I did not have to check each number manually. I just put 2 value of m equal to 3, then I put 4 which failed, then I put 5 which again passed. So instead of doing so many trials, I just did 1 failed trial and 2 successful trials. This is so good. So now what people do, they generate prime numbers using this method only. They 2 to the power m minus 1, if p is prime, it is called a Mersenne prime, because Mersenne made this method. Okay. Now, do you know about perfect numbers? Hello?
Yes, sir. Sir, we don't. Sir, I don't know.
So if you don't know, then tell that also, please. Okay, so perfect number, let me take an example. 6 equal to, not 6 equal to. What are the factors of 6? 1, 2, 3, and 6, na?
Yes,
Now
sir.
if you remove the factor which is equal to itself and you add the rest of them, what is the sum? 1 plus 2 plus 3. This is equal to 6 itself. Let me take another example. 28. What are the factors of 28? 1, 2, 4, 7. What else?
Sir, 14.
14, 28. Bus. Right? Nothing else.
Yes, sir.
Now if you remove 28 and add the others, 1 plus 2 plus 4 plus 7 plus 14, how much is it?
28.
Sir, 28.
Yeah. Now if you check for any other number, for example, you take 15, you take 1, 3, 5, 15. Okay. Now if you remove 15, 1 plus 3 plus 5 equal to how much? 9. This is not equal to 15. So 15 is not a perfect number. But 6 is a perfect number. 28 is a perfect number. Okay. So my claim is if 2 to the power m minus 1 is a prime, then 2 to the power m minus 1 in exponent and 2 to the power m minus 1 is a perfect number. Homework. Prove this.
Can you show the question also?
Question is given only. If this number is a Mersenne prime, then this product will give a perfect number. You have to show this. And how will you show this? How to show perfect number? You have to add the divisors, na? And you know how to add divisors. I just now showed you the formula how to add sum of divisors, sum of factors. This is the formula. So you have to just prove this thing. This is a homework. Acha. Also, uh, Saukarya is here. No, Saptaswa is here. Hello, Saptaswa. Hello.
Yes.
Ha. So, can you make this like if they solve this question, they will get 5 XP points or something.
Okay. I will tell Shogaji about it.
Okay, this question, only this
Okay.
particular homework. If they send you the solution, then give them like how many points that you decide.
Okay.
I don't know. Okay, so this homework has weightage. Okay, so now we are more or less done with this combinatorics aspect of number theory. Everyone copied the question. This question has points, so please copy this question.
Yes, sir. Copy.
Huh. Okay, boss. Now we will learn to solve Diophantine equations. First of all, uh, solve this. Solve this equation.
Minus 2 by 5.
X equal to minus 2 by 5. Okay. Now solve this equation.
Is there any condition given for x comma y?
No.
Sir, then there can be infinitely many solutions.
Yes, very good. So if I have one single equation, one single variable, very simple case, linear equation in one variable, all of you know to say. But if just like if I add one more variable, there are infinitely many solutions. Okay. Now, like there need not even be linear. X square plus 2 to the power x equal to 5. Equation can be like this also. Like basically Diophantine equations are like also since we are studying number theory and like Diophantine equations deal with, let me just write it only. Diophantine, like Diophantus or something was the Greek mathematician. I forgot the name. Let me just Google it. Diophantus. Diophantus is the name of the Greek mathematician. Like he is a very old mathematician,
Problem
like
once.
Euclid kind of. Huh?
Can you please show the homework problem once?
Yeah.
Yeah, okay, thank
Okay. So Diophantus was interested in these equations which do not have a clear-cut solution. How do you solve such complex equations? Not complex means complex number, like difficult equations which you cannot solve simply. How to attack these questions? So these are called Diophantine equations.
Sir,
Huh.
sir, for x square plus 2 to the power x is equal to 5. Sir, I think will it have only one solution? Means it
What
will have one
what
solution.
what is that solution?
No, sir, I was asking, will it have one solution or two solutions or infinite solutions? I was asking that, sir.
I don't know. I just wrote it randomly. I don't know anything about the equation. I have to check. I
Okay,
wrote it
sir.
randomly. I don't know.
Okay, sir.
Acha, so Diophantine equations deal with uh, integer solutions only of equations that don't have a clear cut method to solve. Okay. For example, if I ask you to wait, let me just find a few equations. So let us start with an example. We will continue this in the next class. Okay, don't worry. Here we are giving just an what do I say? Introduction. So, like homework, prove that for any odd integer n to the power 4 is congruent to 1 mod 16. Okay, this is your homework. For now, assume this is true. Now you have to find the equation solutions of find solutions of this for x, y, z, w integers. Okay, so how will you do it? Like, if you don't know anything about number theory, like what thoughts come into your mind when you see such a monstrous equation? Like there is x, there is like there are not one, not two, there
Okay,
are
so I'm telling
four
how to approach.
variables.
The first thing you have to do is just
Wait,
like
wait,
trial
wait,
and error.
wait, wait,
Substitute some
wait,
values
wait,
of x
wait,
and y.
wait. I am not asking for an approach now. I will ask 5 minutes later. So please say 5 minutes later. So like when you see such an equation, there are four variables and there is only one equation. Like you know how to solve these: x plus y equal to 1, x minus y equal to 5. There are two equations, two variables. This can easily be solved. But here I have only one equation, that too with four variables. Okay, now these are linear equations, all the powers are 1. You know how to solve quadratic, but that is also for one variable. This is fourth power, four variables, and just one equation. Like this looks crazy, but still you have been just asked for integer solutions. You don't need to know about real solutions. You just need integer solutions. How will you solve it? Yes, now Sabyasachi say.
Okay, so first you have to see, like just first start by trial and error method. Like suppose just
What?
place a few values of x, y, z and w. Like just place x equals 0 and see what happens. Like if there's three variables and so on. And now second step you should try is to just factorize this 2021 and what you can get this. Now the next thing you should notice is that this is the fourth power. So what is this congruent to towards for something? Like in mod 16 I can write it as rho or 1 in the fourth power. Like as depending on the factors of 2021 you have to find like for congruent to something it has to be equal and from there you should proceed. That should be the best hint for this.
I don't think you even need to factorize 2021. Like there is an even better method. For example, like see for if uh, if n is even, n to the power 4 is congruent to 0 mod 16. If n is odd, n to the power 4 is congruent to 1 mod 16. This you have to prove homework. For now, assume it is true. Now, 2021 is congruent to how much mod 16? Calculate this.
Five. It's 5.
Yeah, 2021. Wait. Is congruent to 5 mod 16. Okay. Now, if x to the power 4 plus y to the power 4 plus z to the power 4 plus w to the power 4 equal to 2021, this thing is 5 mod 16. This can be at most 4 mod 16. Why? If x, y,
Because it can
z,
be the 0
w,
or 1 mod 16. So suppose in all of them are 1
yeah,
mod 16, at most it's 4. So no solution.
yeah, yeah. Like x is x to the power 4 is either 0 mod 16 or 1 mod 16. Okay, similarly y to the power 4, z to the power 4, w to the power 4. Now if all of them are if all of them are 1 mod 16, then also the sum is 4 mod 16, na? Because modulo gets added, we learned in the last class. So LHS is 4 mod 16. Not even 4. Less than equal to 4 mod 16. If one of them is even, then it can be 3 also. If two of them are even, it can be 2 also. So it is less than equal to 4 mod 16 and 2021 is 5 mod 16. Then how can these two be equal? Right? If two numbers are equal, then their remainders with 16 should also be equal, na? Because the numbers only are equal. So everything is equal only. How can it give two numbers dividing with the same number? Understood?
So sir, there will be no solution for x comma y comma z
Yeah,
comma w.
no integer solution. Real solution there might be.
Okay, sir.
Real solution there are infinitely many. It will form a full surface only. All that you will study in college. But we are just interested about integer solutions for now because we are studying number theory. Also, if you want to study real solutions, you need 4 dimensions because 4 variables. So, like for example, x cube plus y cube plus z cube equal to 1. This forms a sphere of radius 1. This
Sir,
is
with
x
center
axis,
0
this is
comma
y.
0 comma 1 plus 0 comma 0
Yeah,
comma 0.
and radius 1. X square plus y square equal to 1.
Sir,
Acha, this
circle
is
with radius 1 with center 0 comma 0.
this is not cube, this is square only. This is square only, I made a mistake. Huh. This is a sphere. This one is a 2D circle. So, like, if you have 4 variables, it will be a 4-dimensional shape. You can't even visualize that. We can only think till 3 dimensions. So, like, let us not study the real roots and all. We are just focusing on integer solutions, and for this equation, there are no integer solutions. Okay. So I showed you how to show there is no integer solution, but sometimes there are solutions and we will deal with them in the next class. Basically, the spirit of this Diophantine equation is like there is no one single method. You have to be creative, you have to make your own methods, you have to try a combination of things, and sometimes I think you have to be lucky also. Like, and you have to have experience and exposure to a lot of problems, then you can solve. I will just teach you some standard techniques, but like there is no particular method to solve these equations. That's why these are so hard and like celebrated. Linear equations to anyone can solve. these equations, you have to think a lot, and then also maybe it is not even solvable. So we will tackle with how to deal with these types of equations in the next class. Okay. So yeah, Sabyasachi, they aren't at all hard in Olympiad because they give you like solvable equations. If you just randomly write something, how will you solve it? Like if I give you x square plus y cube plus z to the power pi plus p to the power q factorial equal to 69. Now solve this. Go. They give you in Olympiads, they give you solvable things. That's why you might feel it is easy, but when you do it in real life, it is not at all easy. And obviously, they are much harder than linear equations. That's why, like, linear equations anyone can solve. Anyways, class is over now. If you have anything to ask, you can ask. And if this meeting ends, I am not starting another meeting.
Sir, I had something to say.
Sir.
Sir, I had proved one HW which you had given last day. It was proved that if A is congruent to B mod M, proves that f of A is congruent to f of B mod M.
Yeah.
Which has integers, means f of x has integer coefficients. So sir,
Yeah,
can I tell
okay.
it?
Tell.
So sorry, I told A is congruent to B mod M. So sir, which implies A is equal to MQ plus B. So sir, which implies A minus B is equal to MQ. This is first equation. Now sir, if I consider f of x is equal to r naught plus r1 x to the power 1 plus r2 x square plus dot 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 rn x to the power n, where r naught, r1, r2 dot 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 rn belong to integers. Therefore, f of a will become r naught plus ar1 plus a square r2 dot 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 plus dot 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 a to a n r to the power a to the power n rn. And sir, f of b will become r naught plus b r1 plus b2 b square r2 plus dot 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 plus b to the power n rn. So sir, now if I subtract both the functions f of a minus f of b, I will get it will become a minus r naught will get cancelled, and we will get a minus b r1 into r1 plus a square minus b square into r2 plus dot 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 plus a to the power n minus b to the power n into rn.
Yeah.
So sir, we know that a to the power n minus b to the power n is always divisible by a minus b for any integer, for any natural value of n.
Yeah.
So
using
sir,
that identity, na? The
yes, sir.
identity I taught last class. Yeah.
So sir, I took a minus b common. So sir, it would become f of a minus f of b is equal to a minus b into r1 plus a plus b r2 plus dot 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 dot
Yeah,
plus
that
a
is
n.
integer. Yeah. Done.
Yes, sir.
Very,
So sir,
very
as a comma b r1 r2 r3 dot 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 rn belong to integers, that therefore that expression which is getting multiplied to a minus b will also be an integer. So sir, f of a minus f of b is equal to a minus b into integer. So sir, f of a minus f of b from equation 1 I will get a minus b is equal to mq. So sir, it will become mq into integer. So sir, f of a minus f of b is divisible by mq. So sir, f of a minus f of b will also be divisible by m. So sir, as m and q are integers, sir.
Yeah, but like wait, let me give you a counter example. No, okay. I was thinking the reverse. Yeah, you are right.
Yes, sir. So sir, it will become, so sir,
done.
f of a minus f of b will become is congruent to 0 mod m. So sir, f of a is congruent to f of b mod m. So sir, where coefficients of f of x are integers, proved. Sir.
Yeah, you are right. Okay, so now another alternate proof is a if the you can just add them, na? like A is congruent to B mod M, A square is congruent to B square mod M,
Yes, sir. Yes,
AQ
sir.
congruent to BQ mod M, then you just multiply each A to the power n and B to the power n with the polynomial ka coefficient and then add
Yes,
them.
sir.
You will get FA on LHS, FB on RHS directly. You don't have to
Yes,
do
sir.
this
Yes, sir.
much. That is the shortcut.
Yes, sir. I
But
could understand it.
your method is also right, and like it is good that you use that identity A to the power n minus B to the power n. Like it is a very
Okay, sir.
useful identity and you will have to use it a lot of times in a lot of problems. So please
Yes,
remember
sir.
that I am speaking to everyone now. Huh. Remember that identity bus. Okay then, if you have nothing more to say, Tata.
Bye, sir. Thank you, sir.
Thank you.
Okay, so I should I'm ending.
Yeah, we can end the session now.
Okay.